The sounds during the intro were different types of noise. We'll talk about these very soon. In terms of music synthesis, noise is a fairly necessary component to do many things. If you're attempting to create a lot of natural sounds such as wind or surf or thunder or lots of other things, a noise source may be where you start, and then you subject it to various types of processing. In addition to that, many musical instruments have a definite noise component. A lot of percussion instruments are primarily noise, though certainly not all. Many percussion instruments are very strongly pitched. And in addition to that, some other instruments, notably wind instruments, also have a noise component, particularly when the note begins. It may not be as well pitched, and there may be a little burst of noise right at the beginning of the note. In fact, in the world of pipe organs, this has a name. It's called a chiff, which is onomatopoeic. And particularly the larger pipes, the lower notes, may have a little chiff at the beginning of each note before the air in the pipe sets up a standing wave. In this video, we will discuss a few different types of noise and their characteristics. The basic noise is usually called white noise. Now, white noise can be characterized in multiple ways. One way is that you can say it has equal energy per frequency range. So if you look at any contiguous 1000 hertz range, whether it's from 0 hertz to 1000 hertz or from 2500 hertz to 3500 hertz, the amount of energy contained in the signal in that frequency range will be the same. In other words, it has a flat distribution. Another way of characterizing this is to say that the amplitude of white noise has a Gaussian frequency distribution. Now, if you don't really know what that means, don't worry too much about it, but for those of you who have studied probability or stochastic processes or communications theory, you will have run across Gaussian distributions before. A Gaussian distribution is what is commonly known as a bell curve. In general, that means that the voltage of your noise signal is most likely to be at the center. Typically, the center is going to be 0 volts, but it doesn't necessarily have to be. And the farther away you get from that center, 0 volts or whatever, on either side, the less likely it becomes. And the way that falls off follows a Gaussian distribution. Now, you may note that we call this white. White is a color. The basic noise types are often referred to by colors. This is sort of analogous to actual colors, where you have red at the lower frequencies up to violet at the higher frequencies. White is a mixture of all frequencies, and that's exactly what white noise is. It's an equal mixture of all frequencies. Another type of noise is called red noise because it contains primarily the lower frequencies. Red noise is also very frequently called brown noise because the probability distribution of the amplitude is essentially the same as the distribution of locations of particles in Brownian motion. You can obtain brown noise by filtering white noise with a low-pass filter with a roll-off of 6 decibels per octave, or 20 decibels per decade if you prefer to look at it that way. The power spectral density of brown noise falls off as 1 over the square of the frequency. We'll compare this to another type of noise momentarily. So that's brown noise. In between brown and white noise, you have pink noise. Now, pink is sort of halfway between red and white, so that makes sense, I suppose. But pink noise can be obtained from white noise by low-pass filtering with a roll-off of -3 dB per octave, or -10 dB per decade. Now, this is a little bit unfortunate, particularly with analog hardware, because getting a precise roll-off in a filter of minus 3 dB is actually not possible, because a single pole filter is going to give you minus 6 dB per octave. But we can approximate that, as we will see later. In pink noise, the power spectral density rolls off as 1 over the frequency, as opposed to brown noise, which rolled off as 1 over the square of the frequency. For those of you who are theoretically inclined, you might find it interesting to verify that the power spectral density dropping as 1 over F does imply a minus 3 dB per octave roll-off, whereas 1 over F squared implies a minus 6 dB per octave roll-off. Now, while we're on the lower end, we've looked at white noise, we've looked at lightly low-pass filtered pink noise, we've looked at somewhat more heavily filtered brown noise. Now, if you filter that even more and filter out almost all of the audio components so that all you've really got left for the most part is sub-audio, then you get what most synthesists call a random voltage. Since it's sub-audio, obviously it is not directly used to create a sound, but random voltages are extremely useful in terms of control signals, whether using it directly or indirectly, as we will see elsewhere in the course. Now, so far we have not really mentioned a cutoff frequency for any of the filters we've mentioned. In general, for the pink noise and the brown noise, you probably want your cutoff frequency to be just a little bit below the bottom end of human hearing, so somewhere around 16 hertz, maybe just a little bit lower. For a random voltage, typically what you'll do is you'll either start with the partially filtered pink or brown noise and add more low-pass filtering, and depending on the characteristics of that random voltage that you desire, you'll probably put another single pole low-pass filter on it, which is going to give you another 6 dB per octave. And the corner frequency you probably want to make a little bit lower, and it's actually useful to make that corner frequency adjustable so that you can have primarily really slow frequencies like 1 hertz or less, or maybe have a little bit more higher frequency sub-audio. So in general, you may want that random voltage filter to have a varying frequency between somewhere around 1 hertz and maybe somewhere around 10 hertz. That's not really a critical issue, and most random voltage sources and synthesizers actually don't have this ability. A few do, but most of them have a fixed corner frequency. Now, those 4 types of noise cover the ones that are most common in music synthesizers. In fact, you seldom find brown noise in synthesizers. You usually will find white and often pink and often a random voltage. Occasionally you'll find brown. There are 3 other types of noise that we're going to discuss briefly here, but you almost never see these in synthesis systems. One is blue noise. It is sort of the counterpart to pink noise in that you take white noise and you high pass filter it with a filter slope of plus 3 dB per octave, and typically you would want to set your corner frequency a little bit above the upper range of human hearing, so in the low to mid 20 kilohertz range perhaps. Purple noise is, in a sense, the counterpart of brown noise or red noise in that its slope is plus 6 dB per octave. And again, it will have a cutoff frequency somewhere in the low 20 kilohertz range. One other type of noise that does have a color assigned to it is gray noise. Gray noise is a little bit flaky, and you really can't properly synthesize it because gray noise is defined as equal loudness per frequency. This gets into psychoacoustics, in other words, how people perceive sound. This depends on the individual. So you can't really have a specific filter characteristic and run your white noise through this one specific filter and it's gray noise for everybody. No, gray noise depends on the person listening to it. But typically, gray noise has a higher amplitude at low frequencies, a higher amplitude at higher frequencies, and a trough in the middle. Now this trough is fairly broad and it's usually centered somewhere in the low kilohertz region. But again, this is not something you can just design a single filter and everybody will then perceive this noise as equal loudness at every frequency. That's not going to happen. That's a summary of the different noise types. In our next video, we will consider the specifications for the noise generator we're going to look at, along with a block diagram, and we will consider how we obtain our original noise signal. There are lots of ways to do it, but in the analog world, there's one primary method, and that will be discussed in the next video.